In this lab, I am using Newton's second law to examine the motion of a free-falling skydiver, Felix Baumgartner, as he falls from 38,969.4 meters in the atmosphere. My objective is to model the motion using Python, tracking him as he falls through the atmosphere in free fall for 36,969.4 meters before opening his parachute. Due to simplifications made in my code, my model did not correctly predict the velocities and positions of Felix as he falls to the surface of the Earth. The fundamental principle used is Newton's second law in the form shown here. The only two forces acting on our system, Felix, is drag and gravity. However, since these forces are not acting at a relatively close distance to the surface of the Earth, these equations are different than what we are used to using and are shown here. With the equations we need to use to find, the final important pieces of information about his trip are found on the Red Bull website and are shown here. With the important data from the jump collected and our equations defined, we can move on to modeling the motion in Python. First, the initial conditions are updated. This includes the initial position, velocity, and the mass of Felix. In addition to this, we also must update other constants that will be necessary in computing the force of drag, which relies on density, which relies on pressure and temperature, and the force of gravity. The drag constant B is found using guess and check to get Felix's final position as close to the surface of the Earth as possible after 540 seconds. Now we can implement the computation loops that calculate the velocity of Felix as he falls and updates the position. The first loop is from t equals 0 to 260 seconds. During this time, Felix is in free fall, so the cross-sectional area is just the cross-sectional area of Felix, 0.2 meters squared. The weight force and drag force have been added in, and since the drag force relies on density, the density equation is added. It is shown that the equation for density is P divided by R times T, and both the pressure and the temperature equations are shown here. In the second calculation loop, Python is calculating the velocities for t equals 260 to 540 seconds, the time in which the parachute is deployed, so the cross-sectional area has increased to 25 meters squared, seen in the AP and the force of the drag equation. After running the model, this is a graph of the position versus time of the positions calculated by the Python code. It can be seen that he falls rapidly, covering most of the height before the parachute is pulled at 260 seconds. Then his position decreases slower as the greater drag force works on him. This is a graph of Felix's actual position versus time for the first 260 seconds. Discrepancies do exist between my model predictions and this data. This is a graph of the velocity versus time from the data computed in Python. According to my model, Felix never breaks the speed of sound. However, the decrease in velocity due to the implementation of the parachute is clearly seen. And this is the graph of Felix's actual velocity versus time up until 260 seconds. The biggest difference between my data and this data is that Felix does break the speed of sound in this model, whereas he doesn't in mine. So why are there such big differences between my model and the actual data? I have made many simplifications to the motion in order to code it in Python. First, motion is assumed to only be in the y direction. However, it is known that there is also motion in the x direction as Felix lands 23 miles away. I have also simplified the model, assuming that all motion occurs in the troposphere, when in real life Felix travels through the upper and lower stratospheres before hitting the troposphere, and the air pressure and temperatures would be different for these areas of the atmosphere, seen here in the charts comparing the upper and lower stratosphere and the troposphere. And finally, I simplified the cross-sectional area to assume that Felix was falling headfirst the entire time. When it is known that Felix was not perfectly straight during his fall, it would spin around. Earlier, I defined the speed of sound at 343 meters per second. This was a minor simplification, as this was the speed of sound in dry air at 20 degrees Celsius. Realistically, the speed of sound depends on temperature, and the initial temperature when Felix first jumps was about negative 20 degrees Celsius. The temperature change versus altitude change graph is shown here. The big difference in the temperatures mean a better way to model the temperature would be using speed of sound equals the square root of the specific heat of the gas times the gas constant R times temperature. With this equation used to compute the temperature, this graph becomes a better representation of the speed of sound versus altitude, speed of sound at altitude versus his velocity. From this, it is seen that Felix breaks the speed of sound at altitude from about t equals 20 to 70 seconds of his fall. If the speed of sound was just taken to be 343 meters per second the entire time, he wouldn't have broken it until almost 40 seconds in. The trick to breaking the speed of sound is to break it before reaching terminal velocity when the force of drag equals the weight force. This is why Felix breaks the speed of sound so early in the trip. Now what would happen if this fall took place on a planet with a much greater density? The density equation relies on temperature and pressure, so a much denser atmosphere would have a lower temperature and a higher air pressure. Creating a model of this motion leads to graphs like these, and although the shape of the graphs is the same, the speeds and the altitudes are much smaller. A higher density slows down the motion, which is expected. The air is denser, so it takes a much greater force to get to the velocities that would be needed to break the speed of sound.